in this video we're going to be looking at the reactions of alkenes and how we can make alkenes from other reactants. So if we take the alkene, in this case I've got butanene, we know that alkenes undergo electrophilic addition, and there's 4 different types of electrophilic addition that we need to know. The first one is known as halogenation, and this is when we add a halogen such as bromine or chlorine across the carbon-to-carbon double bond, and this will form our dihaloalkanes because 2 halogen atoms are added on, which results in a saturated alkane. What we need to know is we need to know the test for unsaturation is that it decolorizes bromine solution. We must be able to draw the mechanism of the electrophilic addition showing the cyclic ion intermediate. And we need to know that the bromine atoms add in a trans formation, that's on opposite sides of the dihaloalkane. This is a 2-step mechanism. The next type of reaction is the addition of hydrogen, which is known as hydrogenation. Now, we do not need to know the mechanism for this, but this will form our family, the alkanes, so we should know this from National 5. What we do need to know, however, as well as the hydrogen, we have to have a nickel catalyst and heat. And because the nickel is in the solid state and hydrogen is in the gas state, this is heterogeneous catalysis. So these are the types of questions that they may ask you. What we can see is over the arrow, that's where we would put our reagents and our circumstances, such as using the nickel catalyst. We can then go on to do the addition of a hydrogen halide. Now this is one of the most important mechanisms that you learn in advanced higher, and by doing so we form the family, the Monohaloalkanes. But isomers can be formed if unsymmetrical alkenes are used, and in this case butanene is an unsymmetrical alkene, so we can form 2 chlorobutane and 1 chlorobutane. You must know Markovnikov's rule. Okay, you need to be able to know that the hydrogen will naturally add to the carbon which already has the most hydrogens attached, and that will be the major product, and the other would be the minor product. But you must be able to explain why this happens by discussing the stability of the carbocation formed in the intermediate step. Monohaloalkanes, we are going to look at, what we can do is we can take those and we can do a base-induced elimination to produce our original alkene. Remember that when we're doing elimination reactions, we must use ethanol as our solvent. And because it's a base-induced elimination, we're wanting to use a base such as potassium hydroxide or sodium hydroxide, as the hydroxide ion acts as a base and accepts a proton. You need to know the mechanism for doing this, and you need to know that you want to remove the hydrogen which is next to the chlorine, and the video of this that I've added as a little card if you want to go back and watch this video. The last type of electrophilic addition that we have to know is the addition of water, which is known as hydration, and that forms our alcohols. Again, we're going to form butan 1-ol and butan 2-ol, as this is an unsymmetrical alkene. And for this mechanism to actually take place, we must use concentrated sulphuric acid. Without that, that mechanism won't happen, as this produces the H+ ions, which act as a catalyst which starts the mechanism. We can take our alcohols and we can dehydrate those to form our alkene. Now for this, what we would want to use is concentrated phosphoric acid, and we tend to use that over concentrated sulphuric acid as there's less side reactions. You don't need to be able to do this mechanism, but I have got a video on that anyway if you want to ensure a full understanding of how this mechanism occurs. And isomers can be formed if a symmetrical alcohol is used. So for instance, if I use butan 2-ol, I could produce but1ene or but2ene, depending on the hydrogen that I'm removing from the alcohol, which can be on either side of the hydroxyl group. We can also use heat and aluminium oxide as well as the heat plus the phosphoric acids.